So looking at the results, they're all again displayed in the table. And we'll graph the results now. First thing we'll plot is the force as before. And then we'll also plot the total current. And make our fonts larger again. And we'll change our axes. And also change the color of the plots to make them stand out better. I'll make the current plot a reddish color. And I'll make it a triangle as well. And make it a little bigger as well. So now you can see what's happening. At the first step, we have the full volume current applied and the same forces we had before. But then with each succeeding step, the amount of volume current drops, and at the same time, of course, the gap is being reduced. So this causes initially a dip in the force, and then the force rises. But remember, there was a range of 5 before, from the maximum to the minimum gap. Now it's a much less of a variation. So that shows an example of how you can use a second parameter in the same loop and also define a parameter by a function. Now, we can combine this idea with our previous idea of nested loops, and in fact we've done this again in the last example we'll show you. So here in this parametric, you notice now we have again the outer loop being the size of the solenoid, and the inner loop has 2 parameters, both the current reduction and the gap. Now I also made a change in the way we're reducing the current in this last example. Okay, now remember before the reduction was based entirely on the step number. Now here once again the reduction is a formula, but it's a function of this variable called gy, and gy turns out to be equal to the y value of the gap parameter. Remember, the gap parameter, there's no motion in the x direction, but the y direction, it varies from initial value of 15 down to a final value of 5. So this is in some ways better, because now instead of basing the reduction on the step number, which you may change, it's now based directly on the y value of the core position. And you can see now, again, at the initial position, you have the full volume current, and then it reduces down to the last position where it's about 0.45 instead of 0.5 as it was in the first formula. And looking at the results produced by this type of reduction, once again we'll use our gap as the x-axis, and we'll use our size as the second variable, so we'll get 5 different curves, and we'll plot the magnitude of the force. So once again we get a family of curves. So each of these curves corresponds to a different size. The bottom curve is for the initial size of solenoid, and then at the top curve we've increased the diameter of the moving core by a factor of 2. And you can see that for each size variation we calculate what is the force at each gap position, and they're much more constant than they were in the previous example. So hopefully from these 2 demonstrations you have a better idea of the power of the parametrics utility and how you can use it in ways you might not have thought of before. Okay, thank you for your time.